Hello, this is Ms. DB. In this video, we are going to learn how to do some of the Chapter 8, Section 1 assignment. This is on factors and greatest common factors. So be sure you've looked over your textbook first, and then when you're ready, on this worksheet, here's some of the vocabulary you need to know. So a factor is a number that divides evenly into another number. So, for example, the factors of 12 are 1 times 12, because that equals 12, 2 times 6, because those equal 12, and 3 times 4. A prime number is a number that has exactly just two factors, no more, only one in itself. So the numbers 2, 3, 5, 7, and so on, these are the first so many primes. A number like 15 is not prime because the factors of 15 include 1 in 15, 1 in itself, but also 3 times 5. So that is not called a prime number. If you're asked for the factorization of a number, that just means to write it as its product of factors. So 3 times 5 equals 15, or 1 times 15 equals 15. The prime factorization is when you break it down into its product of just prime numbers. So we could write, let me do 18 here. You could write 18 with factor trees. We could say that's the same as 2 times 9. 2 is a prime number, so I would stop at 2. But 9 is not prime because the factors of 9 are 3 and 3. 3 is a prime number, 3 is a prime number. That means that the prime factorization of 18 is 2 times 3 times 3, or you could write that as 2 times 3 squared, because we could use an exponent for the 3 times 3. So that's what 18 is equal to. And then the greatest common factor is the largest factor of 2 or more numbers. So if you write out all the factors of one number and then all the factors of another number, the greatest of those is the greatest common factor. And we'll look more at that in a minute. Here's some more on prime factorization, and you're going to do that for this part of the worksheet. Now, one method is to do a factor tree. That's what I just did before. Another method is to repeatedly divide until you can't divide anymore. So that's this latter method. I like the factor tree method. The only thing I don't like about it is it's hard to do when you're typing. So if you want to do the factor trees on your own paper, you could just write the type the prime factorizations here. Or if you want, you could just take a picture of your work and attach it. You wouldn't have to retype it. Let's do number 2. So the way to do the factor trees is first you write the number at the top, and then underneath it you put this little branch, and then you think to yourself, what times what equals 36? Now there's lots of factors of 36. We could do 3 times 12. We could do 4 times 9. I will do, or there's 2 times 18. You just have to pick one. So I'll do 3 times 12. Now when you get to a prime number, you stop. So I'm going to stop at 3 because that is prime. But 12 is not prime because there are factors of 12. So again, you have more than one option. You could say 12 is 2 times 6 or 3 times 4. It doesn't matter. I'll do 2 times 6. Again, 2 is prime, so I would stop. But 6 is not a prime number. So the factors of 6 are 2 and 3. We never write the factors as 1 times something. That's prime then if you can only write it as 1 times something. These are both prime. So the prime factorization of 36, I'm ready to type it now, would be 3 times 2 times 2 times 3. But I'm going to put them in order. So that'd be 2 times 2 times 3 times 3. But that's equal to, I could write these with exponents. So let's see, I have 2 2's and I'm multiplying. So I'll say that's the same as 2 to the second power times 3. And how many 3's do I have? I also have 2 of those. So that's 3 to the second power. So 2 to the second power times 3 to the second power. All right, let's look at one more of these. How about, we'll start number 6. Number 6, we want the prime factorization for 150. Let me give you a hint here. I can say that 150 is 2 times 75, but then we're going to have to go a long way to break 75 down, and you might have a really long branch of your tree, which is fine. But if you want to save some space, try to pick numbers that are close to each other as your factors. For example, 10 times 15 is 150. Then this branch gets a little bit longer, and this branch gets a little bit longer, but you don't have to take up quite as much space. So let's see if all of my bottom row of my branches are prime. I have 2, 5, 3. Those are all prime numbers. So if we're going to type what the prime factorization is, I'll write these in order. 2 times, I have 1 3, and I have 2 5s. So I could write that as 5 times 5, or I could think ahead a little bit and remember that that is the same as to the exponent of 2. Or if you can't find that button on your keyboard and you're typing, remember that you can use this to show that you have an exponent. There it is. So that means 5 squared, or 5 to the second power. All right, let's move on to the next section. This is on greatest common factor, which I told you we'd be talking more about. So the method 1 of greatest common factor is where you list all the factors of both numbers, and then you find the smallest number that is in both rows. So the factors of, the largest one. The factors of 24 are 1, 2, 3, 4, 6, 8, 12, 24. And the reason that those are the factors is because each of these are a pair that when you multiply would equal 24. So 1 times 24 is equal to 24. 2 times 12, 3 times 8, and 4 times 6. All of those pairs will equal 24. So those are all the factors of 24 written in order from least to greatest. The factors of 60, there's really a lot of them. And when we wrote them all out, we found that the greatest that show up in either row was 12. The other method is to write the prime factorization of each of them using factor trees, or just your knowledge of what the factors of the number would be, and then any common factors have to get multiplied together. So there was 2 3s that were common in both of those numbers. Nothing else was common. So then 3 times 3 is the greatest common factor of those two. So you can use either step. Numbers 7, 8, and 9 have to do with method 1, and 10, 11, 12 have to do with either method. I think that most of us have used method 1 more. Method 1 where you list the factors and find the greatest common factor. So if that's the one you're more familiar with, go ahead and use that. And you can also maybe do these in your head if you've done them a lot before and you know if your multiplication facts are really good. So the greatest common factor of 16 and 28. I know that 16 is 1 times 16, of course, 2 times 8, and 4 times 4. You only write the 4 once. I know that the factors of 28, there's not that many, is 1 times 28, 2 times 14, and 4 times 7. I think I got them all. So to find the greatest common factor, it's not going to be 1. 2 is pretty small. Do we have anything bigger? We have 4 and 4, 8, 16. So 4 is the greatest common factor. And again, you can do that work on your own paper if you rather and just write the answers on the worksheet. Or you can just take a picture of your work and not even have to write the answers on the worksheet. All right, sometimes your monomials have variables in them, like in this example. Here in example A, we have 3x cubed and 6x squared. Write these out as the product of primes is easier in this situation. So 3x cubed is 3 times x times x times x. 6x squared is 2 times 3 times x times x. Or the other method for this would be to do that with the variables, and for the numbers, go ahead and write all the factors and find the common factor. Let's look at number 15. So in 15, the factors of 5 are only 1 and 5. Why is that erasing? 1 times 5. Okay, I don't know why, but it's erasing as I write. So the factors of 15 are, or factors of 5 are 1 and 5. The factors of 8 would be 1 and 8, 2 and 4. There's no common factors between either of them. That means the only common factor is 1, and we don't even use that as a factor because every number has 1 as a factor. The factors of y squared are y times y. The factors of y, there's only one, is y. The only thing common in these two numbers, these two monomials, is y. So the greatest common factor for number 15 is just y. That's it. In number 14, there will be a number part and a variable part. So let's see, the factors of 15x cubed. Let's write that out. The factors of 15 are 1, 3, 5, and 15. And the factors of x cubed are x, x, and x. Now let's do the factors of 21x squared. So let's see, the factors of 21 are 1 and 21 and 3 times 7. So if I write them in order, it's 1, 3, 7, and 21. The factors of x squared is just x and x. So what's common between these two? Let's see. We have a 3 in the 15x squared. We have a 3 in the 15x cubed. We have a 3 in the 21x squared. That's all the common ones. We have an x in 15x cubed, and we have an x in the 21x squared. Anything else that's the same? Yes, we could do another x. There's another x in each of them. So I'll highlight that as well. So now I can see that my greatest common factor, GCF for short, would be 3. If there was two numbers, you'd multiply them together. But there's only one in this case, so I put the 3 down. And then I have two x's. And I'm not going to write x times x because we know that 2x's means, x times x means x squared. So the greatest common factor for number 14 would be 3x squared. And then finally you have a problem to do. It's a word problem. It says that Samantha is making beaded necklaces using 54 glass beads and 18 clay beads. She wants each necklace to have the same number of beads, but only one type of bead. So she's going to make some glass beads necklaces, and she's going to make some clay bead necklaces. They're not going to be mixed together. So they're separate. And we have to figure out how many, if she puts the greatest possible number of beads on each necklace, how many necklaces can she make? So she doesn't want to just like put 2 beads on each necklace. So what we need to do is figure out what is the greatest common factor of 54 and 18, because that would be the number that you could use and have the same number of beads on each necklace. So 54 is, let's do 2 times and see how many times 2 goes into 54. 2 goes into 54 27 times. So I can do 1 and I can do 2 and 54 and 27. What about 27? You can break 27 down. So let's see. Let's do 3 into 54. 3 goes into 54, 1. And you can use a calculator to check this too. So it's 3 and 18. 3 and 18. But I don't think I'm done. Am I? Let's get the calculator and double check that I don't have any missing factors. Can 4 go into 54? Can 5? Oh, I bet 6 can go into 54 because 6 times 9 is 54. Now I bet I got them all, but I ran out of room. Okay, so there's a lot of factors of 54. What are the factors of 18? 1 times 18, 2 times 9, 3 times 6, not 4, not 5. So there we have all of them. Now you need to find the greatest common factor that appears in both of these, and that will tell you how many beads you can have. And then you could also answer how many necklaces of each type, how many necklaces can she make, and how many of each type will there be? Will there be 2 clay bead necklaces? Will there be 7 glass bead necklaces? How many will it be if she can have the most possible beads on each necklace? All right, well, that's it for today. Let me know if you have any questions. Thanks a lot.